Okay, this is a kinetics problem. There's some bad math in here. Okay, so the decomposition of gas X to gas Y and Z is represented in the equation below. It's in a 5-liter flask, so this is a volume and this is a temperature. The data, so blah, blah, blah. And then they gave you 3 graphs. This is linear. That's the important thing. I'll get to that in a minute. First question, how many moles of X were initially in the flask? First thing you need to remember is initially means T equals 0. So I'm going to go back. At time 0, it says that the concentration of X, remember X is the reactant, at time 0 is 0.00633 moles per liter. See the moles per liter here. This is not too bad of a problem. So basically we got 0.0063, sorry, I have no idea why that's 0.00633 moles per liter times 5 liters, that's given. Liters cancels with liters, and you end up with, what do you end up with? Oh, 0.03165 moles, and then this has 3 sig figs, and this has 3, and then this doesn't count because it's not sandwich, it's not a final 0, so this is the best answer for A. B, this is a pretty tough problem. I was shocked. I think this is the worst one. It's not horrible, but it's not easy either. So basically what happens on this one is that what you do is if you take the answer for A, which was at time 0, there are point, what was it, 0.317 moles of X. And then that's from part A. That's what this means. At time T equals 20 minutes, so now what's going on at 20 minutes is that you would take 0.00427 moles per liter times 5 liters. And if you do that, you get 0.0214 moles of X. Again, where does this 0.0427 come from? At, sorry, 3 slides back, at time 20, that's the concentration. Now, some interesting things come up here. And so what is the change in the moles of X? Well, it's interesting because it's always final minus initial. So 0.20214 moles minus 0.0317 moles, because remember it's always final minus initial, is that we have gone down this many moles. And if we go back to the first page, that needs to make sense to you, because as this reaction proceeds, the reactant concentration always goes down because X is turning into Y and Z, but the product concentration goes up. And so it should not be concerning. As a matter of fact, you should get some like positive feedback here that between time equals 0 and time equals 20 minutes, that the number of moles is going down. Now, what makes this problem, I think, tough, although you guys, hopefully you're getting good at, because there's a lot of number sense. There is a 1 to 2 mole ratio that Y is appearing twice as fast as X is disappearing. So then the next part of this problem, if this wasn't bad enough, is that we have to say, well, if X is disappearing, the number of moles of X disappeared was -0.130. sorry, negative 0.0103 moles of X has gone, well then 2 times 0.013, and I can do this without a calculator, is 0.0206 moles of Y is appearing. Notice this is positive. This is going down. That's why it's negative. This is coming up. But Y is coming up twice as fast as X is disappearing. But we're still not done because it asked about molecules. And so the most important concept in all of chemistry is the moles. You have this many moles. Well, we happen to know that 1 mole of anything is 6.022 times 10 to the 23rd coulombs. And when I do that on my calculator, I get rounded to 3 sig figs because this has 3. 1.24 times 10 to the 22nd coulombs of Y. And so this is like a mole ratio. If you want to do this a little cleaner, you know, down here, sorry, I probably maybe shouldn't go back and just talk about this a little bit more. So what happens here is that we had that point that X was going down at a rate, sorry, negative 0.0103 moles of X. And then according to the mole ratio, that for every 1 mole of X, you get 2 moles of Y. You know, a little bit cleaner form, and this is disappearing and that's appearing, and so that's why it ends up being this. But there's a lot of number sense on the AP exam, and if you can just explain it, they're usually fine. What is the order of reaction with respect to X? Okay, I have 2 things up to show you. Flipping here, this is the 2015 formula sheet. This is kinetics. If you remember, this is the equation for a first order, and this is an equation for a second order. These are the only 2 formulas. A 0 order is this one with the LNs taken off. I have never seen a 0 order on the test, but we're supposed to teach it. So first order, second order. And so what happens is we're going to use this equation over and over and over again in the next couple parts. If I go back, what is the order of the reaction with respect to X? Well, that's this. It's this easy. If you graph ln at X versus time and it's linear, it's first order. If you graph the reciprocal of X versus time and it's linear, it's second order. This is not linear. If you graph X versus time and it's linear, it's 0 order. So the one that's linear determines the order. And so this is 0. They call it 0th order. This is first order. This is second order. And if you remember the lab with crystal violet, where we were measuring how fast the purple color, the violet color was disappearing, it was also first order, because that's linear, it's first order, and it's really this easy. It is first order. Why? Because the graph, and remember how we title graphs in chemistry, it's Y versus X, of the ln of X versus time is linear. So it is first order. That's why they gave you those graphs, that easy. What is the rate law? Well, order means exponent. So the rate law is K times the concentration of X to the 1 power. That easy. What's the rate constant? Now I need to go back. And so what happens is I'm going to take the first 2 data points. I'm going to write them down here, and then I'm going to go back and show you where I got those. The first 2 data points are, so time versus concentration of X. So the first data point is 0.00633, and the second data point is 10, 0.00520. And I'm just going to go back and show you at the very beginning. You can just flip your thing over. This is where I got those numbers. These are the first two data points. And so now, because we know it's first order, we go to our formula sheet. Sorry, I'm right here. Back to this formula sheet. I'm going to grab this equation. I'm going to change A's to X's because in our specific equation, the reactant isn't, or sorry, the reactant's not called A, the reactant's called X. And so what happens is I know, let me just do here, y equals mx plus b. The natural log of x at any time is equal to negative kt plus the ln of x sub 0. That's the equation. I'm going to switch colors here quickly. Notice that they want us to solve for k. So the first thing I would do is put this over here, and then I would divide both sides by negative t, and I would just do the math ahead of time. They don't really do that on the scoring guidelines, but that's what I would do. The ln of x at 10 minutes minus the ln of x at 0 minutes divided by negative t equals k. Okay, so I took this over here and I divided. Now what happens is you can just plug this into a calculator. So this is going to be the ln of 0.00520. See that? Minus, sorry, make sure you close that on your calculator. Minus the ln of 0.00633 divided by the elapsed time, which is negative 10, equals k. And this is the one time that you don't have to do the factor label method in chemistry because the ln does this. I'm just going to plug this in my calculator. I wish I could just pull up my calculator. Make sure you do that, close the parentheses, minus that, hit enter so that it takes the whole answer, or else use parentheses up here. But k comes up to be, on the scoring guidelines, they have 0.0197 per minute, and I'm going to talk about that, why you need to put that minute in there downstairs. And so what happens is I don't agree with this, because when I look at this right here, I see 2 sig figs. I do not know why they're keeping 3. So in my opinion, but remember on the AP exam, you just have to be within 1 sig fig of the right answer. I think the best answer to this question is 0.020 per minute. Now let's talk about the units. Okay, remember how this is first order? So in a first order equation where rate equals k times the concentration of x to the first power, well, k is always going to be rate, which is always in molarity per second, or sorry, in this case it's minute. Molarity per minute, divided by, so k is equal rate divided by the concentration of x. Well, the concentration of x is molarity, and that would cancel, and so you'd get per minute. But the other thing is we said that it's always 1 less than the order. So the exponent on the molarity is 1 less than the order. Well, what's 1 less than 1? 0. And that's why k ends up being that. And then this is probably the second hardest part. What's the concentration after 150 minutes? So the natural log of t equals negative kt plus the ln of x sub 0. If I want to solve this for this, I would take e to both sides. So basically, the concentration of x at the time 150 is e to the negative kt plus the ln of the initial concentration. And so and I'm just going to have the calculator do the work. We figured out in part E that this is 0.020, but I have to make it negative, and then times 150 plus the ln of I think it's 0.00633. Okay, let me just check that quick. I can't remember where I wrote this. Yep, perfect. And so then you just do this on the calculator. So E caret, it knows that it needs to multiply before add. Make sure that you have double parentheses, one on the outside of the ln and one to close this. And then to 2 sig figs, because this only has 2, so 3.2 times 10 to the negative 4. And since you're solving for concentration, you have to slap an M on it. And that's it.